Swayam Prabha. Digital India. Educated India.
So, in the last class what we did was, in the last lecture, that we tried to work out the integral formulations of the mass and the momentum equations. Okay. So, the point that we stopped was that we defined that how the continuity equation or the mass conservation equation can be written, and we also proposed the momentum equation in its integral version. Now, remember in those equations, okay, we defined that there is a body force term, okay, which is strictly given by x k I. This is a continuation of last lecture. Now, the body force term, in most of the cases it is gravity. Okay. So, if it is gravity, the body force term is reduced to a form like this. Okay. So, the stress tensor, this is the body force term. Okay. Now, the other forces that are acting on the control volume, on the fluid control volume, okay, includes both the normal as well as the shear stresses, right. So, shear stresses, we know what shear stresses are, okay. So, from your undergraduate fluid mechanics knowledge. So, it is the total force is basically nothing but the sum total of the body force and the total stress. So, tau k, this particular thing is nothing but the total stress tensor, and n k is basically the local normal unit vector. Okay. So, the total momentum equation therefore can be written in this particular form. Okay. So, what can we say? This particular term is a rate of change of momentum within the control volume. This is the momentum flux. Basically, these two constitutes the convective derivative portion. This is nothing but the body force term, and this is the total stress term. Okay. So, this is nothing but Newton's second law. Okay. Law of motion. Got it. Now, if the control volume includes multiple phases, if you recall that particular diagram where we had say 3 phases. Okay. So, this is like your control volume. 3 phases, say this is liquid, this is vapor, this is solid, these are basically the areas. This can be actually 3D, and this is the volume. Okay. Now, if it contains multiple phases, then you need to perform this integral form for each of those sub volume, right. So, sub volume means this is one sub volume, this is another sub volume, that is another sub volume, right. So, if the phases are very well separated and things like that, you can actually have these two as your sub volumes. Okay. Got it. So, that is an interesting assumption over here, that the control volume is occupied by several phases. In this case, it is solid, liquid, and vapor. Okay. So, when it is solid, you have the solid part, which is the solid part of the control volume. So, when you actually perform integration over multiple phases, this is the final form of the equation that you get. If you look at this form, there are a couple of things. The area AK is basically the individual areas, the individual control surface. For example, if I look at this particular diagram once again, you will find if I take this out, this is for example the area of the solid. Okay. If I take that out, this particular area out, this is like the area of say the vapor, right. So, this is that area that we are talking about. Okay. Similarly, this volume are the individual sub volumes, the rest of the equation remains exactly the same, right. The rest of the equation is nothing but this, but it has been summed over all the phases. Okay. So, that is the momentum equation that we did last class. There we have re-emphasized and said that what the momentum equation should look like. Now, let us take a look at the energy equation. Okay. The energy equation is basically nothing but the first law of thermodynamics for a fixed mass system, right. Okay. So, what is the first law of thermodynamics, we did it in the first lecture. It is nothing but the rate of change of energy of the system. This energy includes the internal energy, kinetic energy, potential energy, any surface tension or other such energies that can be there. Okay. Most of the time we are concerned with internal energy. It is nothing but the heat and the work transfer, right. These are the other two terms. This is the typical first law, right. For a control volume that contains only one phase, because that is the methodology that we are following, we are defining it for one phase and then we are showing that what kind of if we take it across multiple phases, what will happen. So, now the property function that we defined in the last class is nothing but the energy plus this kinetic energy head, okay, and the corresponding small phi k is nothing but the intensive version of the same. Now, if we substitute the value of phi k in the governing equation, right, the equation that we established, we see that the rate of change of energy within the system, it looks very familiar to like a conservation equation. It basically tells you the rate of change of energy within the control volume and whatever is the flux that is happening, okay, across the control surfaces. So, these are basically the internal energy and the specific internal energy, capital E k and small e k, right. So, substituting this over here, where we are bringing in the q k and the w k term, the same expression is kind of valid, right. Okay. So, here we are proposing something which is a little bit interesting, that this particular term, which is nothing but the heat transfer across the control surface, right, that we are proposing that can happen due to two ways. Okay. One is basically due to the internal energy generation inside the control volume, right, and the other one is basically the flux that is coming due to conduction, right. Okay. So, this q k double prime into n k dA is nothing but the conductance, it is like a heat flux vector at the control surface, control volume surface, right, and q k triple prime is nothing but the internal heat generation, right. In the case of work term, now if we look at the work term over here, now this work term is nothing but the work done by the normal and the shear stress and by the body force, right. So, we already saw in the momentum equation that there was shear stress and then there was body force and then there was normal stress. So, this is the nothing but the work done by all those forces. So, naturally by the total stress, the work done by the total stress is given by this. Okay. Similarly, the work done by the body force is given by this. Okay. So, these are the two work related terms, body force and by the normal stress, okay, and by the shear stress on the control volume. So, for a single phase, therefore, assembling all these parts of the equation, we get this final form. Okay. Now, in this final form, if you take a closer look, you will find that once again the first two terms are basically your advection term or convective term. Okay. The first term on the right hand side designates your diffusion term or the conduction term, right. This is the internal energy generation term. This is basically the work done, these two are basically the work done component, okay, by shear, normal stress and body force, right. Okay. For multiphase, what we do? We follow the same exercise, that we sum all these components, right, across all the phases over here, but with a special attention that this V k is nothing but the individual sub volumes. V k is basically the sub volume of each phase. Similarly, A k is the surface area of each phase occupied by each phase, okay, and basically we have summed over all the phases. So, that is the expression that you see. So, the energy equation basically, as you already knew from your undergraduate, is basically consists of the advection term, the conduction term, the heat generation term, the work that is done due to the shear stress and the normal stress and the work that is done by the body force. Okay. So, that is basically nothing but your energy equation, right. And this energy is basically the component sum together of the kinetic energy component and the internal energy component. And you can, here we have of course neglected potential plus any surface tension related component, those we have neglected. Moving on. So, we have done basically the conservation of energy, conservation of mass, conservation of momentum. Now, let us look at the second law of thermodynamics, right, applied to a system with fixed mass and containing one phase only, because that is how we start. Here of course, the variable, the property is basically nothing but the kinetic energy of the kth phase, right. So, this is the extensive quantity, this is the intensive quantity. Okay. So, how do you write it? Once again the same expression is valid, right. The rate of change of entropy in the system is given by the rate of entropy within the control volume plus whatever is the entropy that is coming out, right, through the control surfaces, right. Okay. So, the change of entropy in a closed system results from heat transfer and or entropy generation, correct. So, the entropy change in the system happening due to heat transfer is given by this expression. The entropy change due to the heat generation is given by that expression, and then there is of course the entropy generation term, okay, itself. So, what is this particular term? This is essentially the heat transfer across the control volume or control surface. Okay. This is basically nothing but the entropy generation due to volumetric heat, and this is the normal entropy generation term which has to be greater than 0 basically, is S dot triple gen. Okay. Now, for a single phase therefore, if we put all these parameters together, you will once again have that there is a convective term, okay. There is a entropy that is generated or the entropy, the change that happens due to the heat transfer across the control surface, entropy that is generated due to volumetric heat generation, and this expresses the extent of the irreversibility, right. So, there is an entropy generation in the control volume. So, this entire thing is greater than 0, that is because the generation term is actually greater than 0, right. You do it for multiple phases, it is the exact same expression that we have. Okay. Once again, only thing that is taken care of is AK and VK, AK and VK. These are the only two things that you need to take care, right. So, whenever you do, you are doing it for the particular sub volume and the sub control surfaces essentially, right, and you are summing them together and you are summing the entropy that is generated in each of the phases, okay, and then you show that this has to be greater than equal to 0. Right. So, this is basically the second law of thermodynamics when you cast it in a control volume approach. Okay. So, I think this should be pretty clear, right. There is always a rate of change of that particular variable inside or that property inside the control volume, and then there is a flux term. These are the two universal things. Okay. Now, in addition to that, we are stating that this should be related, the entropy change is also related to the change of due to heat transfer, heat generation and the normal generation because of the irreversibility of the process. So, this is due to irreversibility. Okay. So, that is what this particular term is. Now, we look at the final thing, which is nothing but the species balance equation. Okay. Species balance, why the species balance is important? Because species balance equation, as I said, if it is a single component system, it does not really matter. Okay. But if it is a system which is a reacting system, like for example a combusting system or any other similar type of system, species actually do play a major role, right. Okay. So, if the system contains one phase and more than one component, that is how we start a single phase multi component system, the total mass of the system is composed of multiple species, correct. because it may be air, nitrogen, CO2, there may be thousands of species that may be present. There is no limitation as to the total number of species that can be there. Okay. So, here the phi k now that we define is basically nothing but the mass of the ith species in the kth phase. Okay. So, this mass m k I is basically the mass of the ith species in the kth phase. So, say for example, it is water, that means it is the mass of water in whatever phase it is present in. Then there can be air, so it can be mass of air in whatever phase it is present in. Okay. So, similar thing when you, and actually the small phi k is nothing but the variation in the density. So, this is the density of the ith component in the kth phase, okay, and this is the total density or the average density. Okay. So, now when we write the change of mass of the ith component in the kth phase in that particular system, once again it is composed of two components, right. So, one is the rate of change of that particular component within the control volume, the other one is the flux term, right. Remember here the velocity is V k I relative. That means, this is the velocity of the ith species in the kth phase, this is the relative velocity basically of the ith species in the kth phase, okay. And this rho k I is nothing but the density of the ith species in the kth phase, okay. So, if there is no chemical reaction for example, okay, the total mass of the ith species remains constant, right. So, it is exactly like a continuity equation, right, because if there is no reaction, say for example, in a vessel, okay, you have water vapor, air, CO2, nitrogen, everything you have put together like this room for example. Okay. This is a multi component system room, but here you do not have any chemical reaction, right. So, if you do not have any chemical reaction, the total mass of the ith species remains constant, right. So, species wise, okay, it is almost like a mass conservation. Chemical reactions on the other hand, if it happens, it leads to the production and consumption of the ith species, right. Say for example, if you have a reaction C plus O2 and form CO2, right. What happens is that there were two components C and O2, they are consumed and you create CO2 in its place, right. The total mass is still conserved, right, the total mass is still conserved, that we already know, but individually the species mass are not conserved. Okay. So, the C and the O2, if this is a vessel which initially had C plus O2, okay, after some time you will get the same vessel where there will be lot of CO2 and very little C and O2. It will be still there, but it will be in very small quantities, right. So, if you started with 1 gram of C and 1 gram of O2, you might end up getting say 0.1 gram of C and 0.1 gram of O2 or something like that, okay, because the rest has been converted to CO2. The mass is still conserved, okay, but the mass of the individual species are not. So, it leads to production and consumption of the ith species, which needs to be cast as a mass source or sink term. Okay. So, like for example, take a look at this particular equation over here, right. So, this is the rate of change of mass, okay, of the ith species in the kth phase in the system, and that can only be given by some kind of a sink or source term. This m triple prime k I dV is nothing but a sink or a source. It can be a depletion, it can be a production also, right. So, for a single species, it looks very familiar to a mass conservation equation, except that in the mass conservation equation this term basically goes to 0, but here in this case obviously you are not going to have that, okay. Taking into account chemical reaction, you produce mass within the control volume, right, rate of mass production within the control volume, okay. But note one other thing, the rate of production or consumption of mass of the ith species and all the species combined has to be equal to 0, because globally the mass has to be conserved, right. So, say for example, here C, the concentration of C or the mass of C and the mass of O2 may be coming down, but the mass of CO2 actually increases, correct. Mass of CO2 increases, the mass of C and O2 actually drops, okay. So, here what we can see is that the rate of production or consumption, the total rate of production or consumption of mass is basically 0, okay. And one other thing is that the density, the total density is nothing but the sum total of all the density of all the individual components or the individual species, right. So, for all the n species you just need to sum together this expression with correspondingly over n. N is the total number of species, not the number of phases though. And this V k relative, which is the relative velocity or the bulk relative velocity of a multi-component system, is nothing but the density weighted. Okay, it is the density weighted, it is rho k into V k, right. So, it is a density weighted summation of all the individual species of the system, right. So, that is why that V k can be written as 1 over rho k, okay, summation of I equal to 1 to n rho k I into V k I relative, right. So, that you can say from this particular expression, right. So, it is nothing but the density averaged velocity of each of the component. So, that is the species balance in a nutshell, right. Now, if you look at this particular expression over here, it is not complete yet, say the second term on the left hand side, okay. The second term on the left hand side, this represents the species I mass flow across the surface of the control volume, which can result from convection of the bulk flow as well as diffusion with respect to the bulk convection. So, one can be due to bulk convection, right, okay, across the control surface. So, species I moves across the control surface, that may be due to the velocity that it carries by itself, right. It could be also because of the diffusion on the top of that bulk convection, is not that so. So, if you write this expression, you will find that there is a component which is V k relative, that is the relative velocity, that is the kth velocity, okay. So, that is like the bulk, this is the bulk, right. And there is another component which is given by that j. J is basically the diffusive mass flux vector of species I in the kth phase. Okay. To understand this, basically what we have done is that we have said that the species is getting transported across a control surface, right, good thing. Now, this transport of species across the control surface may be happening due to the convection of the bulk flow. Bulk flow is V k relative. So, this bulk flow carries with it, okay, a certain amount of species. So, this is a control volume, there is a bulk flow that is going out, which is given by V k relative, right. So, as it is flowing out, it is carrying the ith species with it, right. It is carrying the ith species with it, okay. But on the top of that, if there are concentration gradient across the flow field, right, it can happen, right. So, from here, say for example, the concentration of species I is higher than here, right. So, there will be a diffusive transport, okay. It is like a conduction problem. That means, when there is a temperature gradient, there is a heat flow. Here, when there is a concentration gradient, there is a corresponding species flow. That is not the bulk flow that we are talking about over here, okay. So, that is given by this J, okay. So, the diffusive mass flux vector. So, now what we have is basically we have a convective derivative fully, we have a diffusion term, and we have a corresponding production term. So, this is diffusion, this exactly looks like a heat balance equation. This is the basically the convection, advection, whatever you call it, and this is basically production or sink kind of a term. Now, for multiphase systems, what we do is basically we, for each species, this is for each species, right. So, each species may be present in in at least 2 phases. So, there you sum total it over each of the individual phases, right. Once again A k, the V k comes into the picture, right. So, this is nothing, it all remains the same, except that, okay, we are having a transport of the each species as per this particular equation, right. So, in a multi-component system, that is what happens. This is the term that is solely reserved for reaction basically, got it. So, I think in this particular slide what we have explained over there is that you not only have a convection, but you also have a diffusion of species, because you can have a concentration gradient, because there are many species that are present in the system, and you also can have a production or a destruction kind of a term of the species. Okay. And you have the similar, this looks exactly the same like a mass balance equation, like a continuity equation, only this term is new and this term is new, but this term looks familiar to a heat conduction equation. It looks very familiar to a heat conduction equation, right, looks very familiar to a heat conduction term, right, that you have in the energy equation, right. At the same time, okay, so this heat conduction equation is very similar to heat conduction, except that instead of temperature gradient you have a species balance gradient over here. Okay. So, this completes the species balance part of the thing. Now, in most of the time we basically deal with instead of integral formulation, we deal with differential formulations, right, because differential formulations are sometimes easier to handle. Now, all of these can be derived from the integral formulation as well. Now, for the differential formulation, it is necessary first to apply the divergence theorem. What is the divergence theorem? This is basically any property that you can think of. Okay. So, that property, okay, which is enclosed by a control volume, this is a control volume V, which is basically enclosed by a piecewise smooth control surface. So, basically what we can do is that this area integral can be converted to the corresponding volume integral, right. So, this is nothing but the flux of whatever is the quantity that you are dealing with, right, with respect to the surface normal, okay, of the enclosed area. Now, if it is piecewise smooth, okay, then this is related to the divergence of the same component, okay, on a volume basis, right. And furthermore, since the control volume shape and size are fixed in space, we can apply Leibniz rule, okay, for any specific general quantity, and we can say that this is the formulation. This Leibniz rule you have seen in the case of your boundary layer analysis also, right. So, it says that if it is control volume is fixed, shape and size are fixed in time, right, we can cast the rate of change of whatever is the property over here, and we can take this basically within this integral sign. Okay. So, the conservation of mass, basically what does it become? Initially this was these are the two reduction terms, like for example, the flux term in the case of conservation of mass, that is the flux term across the control surface, is now converted to the corresponding divergence, right, the divergence of this particular quantity, right. And what happens is that if we apply now, okay, this transformation, everything now is on a volume basis, right. The integral now becomes only with respect to volume, there is no area. If you just quickly take a look what we did earlier, you will find that here, for example, take a look at this particular expression, right. Here we see that there is an area basis, right, and this is the one that is on the volume basis. Now, what we have done in this particular case is basically we have converted that area integral to a volume integral, correct. So, using the divergence theorem, right, and we have taken now, and then using Leibniz rule we convert the continuity equation to this particular form, correct. Okay. So, for now if you see this integral is basically equal to 0. Now, since it is valid for any arbitrary shape and size, that means you can shrink the control volume, okay, with impunity to as small a size as you want, right, then the integrand must be also equal to 0, right. That means the integrand must be also equal to 0, because it is valid for any control volume, right, no matter how small or how large it is, right. So, Integrand equal to 0 means this particular term becomes equal to 0, right. So, this is the standard continuity equation that you may have seen in your undergraduate or first level graduate courses. Okay. So, this can be basically written by a material derivative, okay, d rho k by dt plus this divergence component, right. So, this is basically by the divergence of velocity that we have, right. So, it is basically this d by dt is basically nothing but the material derivative, as I said just now. It is composed of the time derivative plus v k relative into the corresponding operator, right. So, this acts on the density, right. So, now if it is an incompressible flow, say for example, that means the density does not change, we only get the divergence of velocity to be equal to 0, right. So, that is why in many of the problems that you solve, you find that the divergence of velocity is always equal to 0 for incompressible flow. However, for steady state compressible flow, it is not the divergence of velocity, but the divergence of this that is actually equal to 0, right. Okay. So, this shows that how easily we can convert an integral formulation to a corresponding differential formulation just by using the divergence theorem and the Leibniz rule, okay, nothing else. Okay. So, in the next class what we are going to do is that we are going to take a look now at the momentum equation. Okay. So, we will stop here and we start in the next lecture where we will look at the differential formulation of the momentum equation.